Today the lecture will be how to use quantum espresso, or in general first principle method, to simulate vibrational spectra. So we will consider vibrational spectroscopy. Some example of vibrational spectroscopy. So the lecture will be like this. First we'll just do an introduction, no? to see which kind of methods can be used to measure phone properties, vibrational properties. And this will lead to discussion of how phonons are coupled with the macroscopic electric field. Macroscopic in the sense compared to the length of the primitive cell. No? And then we will focus on to measure vibrational spectroscopy, which are very widespread in laboratories, and for which is interesting the possibility of calculating simulating the spectra by first principle. So we consider infrared spectra, and then Raman spectra. And this is just the end of the first theoretical part. And then we will see how we can calculate, let's call the ingredients of the tensor and the matrix we need to calculate infrared Raman spectra on first principle, and in particular using the quantum espresso. It will be quite general. And we will treat in particular two things. First, how to calculate then from a linear response. This is a theorem that maybe you know that will be the 2n+1 theorem. And then how to calculate them with the so-called Berry phase formulation for the polarization. And we also introduce this concept for you already heard about this on the talk of Nicola 2 days ago. So this is what we will do. So let's start. So there are several methods for measuring phonon properties, and I selected some of them. So first of all, you could think about using neutrons. Neutrons have a property that is quite useful for measuring phonon properties. This property is that they carry no charge, no? So they don't interact strongly with electrons. So they are essentially the spectra that already you've seen in the sequential propagation theory talk were recorded by neutron scattering, elastic neutron scattering. The problem is that if you want to measure phonons with a neutron, you need a neutron source. That's something that is not easily available at a lab. There are other two spectroscopies that are easily available in lab, also quite inexpensive, and have a lot of experimental work is done using these two techniques. The first one is using infrared light. No? So infrared light will be infrared, so light at a frequency which can, at the same frequency of, or comparable frequency of the vibrational eigenmode. So the light will couple directly with the phonons, and then we can measure the absorption, the reflectivity, the energy loss, and also most of you have already heard this term, Fourier transform infrared spectra, infrared absorption spectra is one of the I think most popular way to measure infrared absorption spectra. So this is very important. And then there is another technique that I think everybody already heard here about Raman. And in Raman, so we don't use infrared light. We use light usually at the visible, around visible frequency. So at a frequency which is higher than the frequency corresponding to those phonons. And here we consider the inelastic scattering of light. And we will see that this is modulated by phonons. They can be either created or annihilated. There are a lot of different techniques based on the Raman. One is called a resonant Raman. We should not treat today. Resonant Raman, the frequency of the light will also couple with the frequency of an electronic excitation. Very important. And then also maybe you have read the term Schumpeter's enhanced Raman scattering. So with a molecule on a surface, it's possible to perform Raman measurement. We can detect which have an enhancement factor of several order of magnitude. In some cases, you can detect single molecules. And also, we will not speak, but it's possible to do also quantum espresso. We can calculate a non-linear Raman response, which is called hyper-Raman. This also can have a resonant flavor. But in the talk, we will just consider the simplest non-resonant Raman case, in which the light which is used to measure the spectrum is at frequencies which are below the electronic excitations. Okay. So, in this talk, we will not consider further neutron spectrum. It's quite interesting how it's possible to, in particular the case for disordered materials and formed, for example, and for liquids, particularly interesting how it's possible to simulate the outcome of the experiment, so the spectrum, but we will not consider this. We focus instead of infrared Raman processes. So the first things we notice is that we are using, we are in the experiment, light source, which is the laser, which corresponding wavelengths are much bigger, much larger than the periodicity cell of the material we are studying. No? Because light is the order of microns, and here we are order of nanometer or something like this. So locally, no, you can see that the electric field, which is felt by the electrons, can be considered macroscopic. No, it's very important. And then we will note another things that the corresponding momentum is very small. So both in infrared and Raman spectrum, only phonons which are close to the common point will be involved in the process. In particular, we will see what close to the gamma point means. It's something that you already heard when we are considering the fact that the dynamical matrix of the phonons and also the phone you calculate have an analytic term at the gamma point. So this close to means that a direction is the direction is important. Okay. Okay, here. So my idea is like this. First, we introduce just a simple model to calculate all the formalism, in very simple model. Then this formalism will just extend in the general case. We will see the formulation from infrared and Raman scattering, and then we will see how the matrix that we are introducing now can be calculated by first principle. So here we consider this is one of the best books about coupling of crystal with electric fields. And we can see a very, very simple scheme model in which so we have a cubic crystal, polar, which is polar, no? So we need the dipoles in order to couple with electric field. We consider the relative displacement respect to the atom, no, respect, of course, the equilibrium position. And here we can notice we use this complex notation. Of course, we can use the real one, but this is just for simplicity. This Q is intended to be the momentum, no, of the electric field. Just consider this will be the static limit, so we don't consider magnetic field. And this Q is very, very small, so it's very close to the center zone. this will be important to study the electrostatic of this system. So now, this is how we can describe the relative displacement of two atoms, and now we need a formulation for the energy of the system. So center zone, no, you know that you expect to have 3 acoustic mode, no, and 3 optical one, and now we want to consider the coupling, the optical one with the electric field. This is just to introduce the formula. Okay, this is the energy term, no, that we want the model we want to build. So the energy will depend on the relative displacement and of the electric field. This is a big. So without electric field, we would have a term which is like this, just the energy of the string, which is oscillating with the frequency which is omega. Then we just think at a system which is not oscillating. So we crank down the position of the two atoms. We will have the energy of the system will depend by the electric field in this way. And then we will have a coupling of the two atoms with electric field can be written in this way, in which there is a coupling of a dipole, and that this dipole is written as a product of the relative displacement time a factor, and this factor has the name of Born effective charges. Okay, this is the model. Then see, as you see here, there are 2 different contributions to the electric field, and one is the contribution that is to the polarization, which is given at the position of the atom which are kept fixed. This is the electronic contribution to the polarization. It is written in this term, so it's proportional to the electric field with the factor with the electric susceptibility at high frequency. High frequency means that at frequency which are higher than the frequency of the vibrational modes. And then we will have a ionic contribution, which is the dipole that I've spoken before. No? In these 2 terms, gives the sum of the 2 terms gives the polarization induced by the electric field.
The wave numbers Q in displacement and electric field are same?
Yeah. Yeah, it will be the same.
So when is the response to external electric field will be the same wave number?
Yeah, exactly.
That's the assumption.
We want to study the coupling of electric field, so the electric field will cause the. Okay. So it's there, because it's also the linear. Okay. Now we can consider the relative force acting on the 2 atoms. We just to take with the minus sign the derivative of the energy, the model from the energy we produced divided by the take with respect to the relative displacement, and we have this formula here. So we have the expression for a string we already know times a coupling of the electric field with the Born effective charges. And now we can from electrostatic we can have the formulation from induction, which can be found from in this way. The induction is just given by the electric field plus 4 times pi, and the polarization we have described before. Okay, this is in Gauss. And just remember that from the electric susceptibility, we obtain the electric constant, then we will see that these are becoming matrix with this relation, which is written as this. Okay, so we take this formula here. We take this definition here, it is already written, and the result, and finally we obtain a formula for the electric induction, which is written in terms of the quantity charges and of the high frequency dielectric constant. Okay. Now, these are the simplest case.